in representation theory of finite groups. So we have a finite group and a prime P. So one of the main problems is to count, if possible, certain irreducible characters of G locally. And locally, okay, I write it like this because there is nothing, I have not defined local. But in our understanding, local means related to P subgroups, and they are normalizers. So local, we understand that if P is a P subgroup, we don't want P to be trivial. We understand that normalizers of P subgroups, centralizers, they are intersections. They are local subgroups. I will try to make a more formal definition, but for now, from now on, it's okay. And the other thing that I was trying to tell you the other day was that there is a special kind of irreducible characters which are called p-defect zero characters. So chi has p-defect zero if the p part is as large as possible. And as I told you, Richard Brouwer asked, one of his problems was to count how many defect zero characters are by group theoretical means, and this was solved by Jeff Robinson. Okay, so we stop there. Okay. So now we want to start with the other extreme. What is the other extreme? The other extreme is are characters whose p part is as small as possible, meaning 1. So these are what we call the irreducible characters of p prime degree. The p part being 1, this means that p doesn't divide chi of 1. Richard Brouwer was very much interested in p-defect zero characters. We saw some of the properties the other day, but he was also very interested in these characters, the height zero characters, if you know about blocks. So he really was thinking about Brouwer characters. So for me, it's a mystery how he missed the Mackay conjecture, because it's once you start doing examples and you realize that there is something very important and very deep going on. Okay, John Mackay is a mathematician that everybody knows that is perhaps famous for two celebrated observations. One is the monstrous moonshine that gave Richard Borders downstairs the Fields Medal. And the other, I think, great observation by John Mackay is the Mackay conjecture. I have talked a lot about the Mackay conjecture and has been mentioned here, so I will go very fast through the Mackay conjecture, but I feel that perhaps some of you do not know that, so let me repeat that. So the Mackay conjecture asserts something amazing, which is that the number of p prime character degrees of G can be computed in the Zillow normalizer. For those of you that were asking me the other day about what is local, this is a local thing. I mean, just the number of p prime character degrees, you can compute it in a local subgroup. there is no words to explain how amazing this conjecture is, in the sense that these two groups are so different, and still they share this important invariant. G can be the monster, P equals 2, and this is a huge 2 subgroup. But so what? I mean, so there is something. There should be a beautiful proof of this, but we don't know how to even start. Well, we know how to start, but I mean, we don't have a conceptual proof of this. This is wide open. And the other day, after the wine reception, I was thinking about a metaphor to tell you about how impressive the Mackay conjecture is, and they came up with the following, which right now, after the wine, I thought it was a good one, but now I don't think it's such a good metaphor. But anyway, what I'm going to say is that for me, this is like if you are watching a football game, and at halftime, you know the final score. I mean, this is amazing. I mean, this is just not even halftime. This is at the beginning of the game, you know that, and suddenly you know the final score. This is like it is. Okay, anyway. So let me just very briefly tell you that we don't know how to prove this in a conceptual way. And for instance, you are in p-solvable groups. There's a wonderful way to prove this using some arguments by Okuyama and Wajima. Fantastic. If you are into symmetric groups, there are some arguments that you do by Olson. Wonderful arguments for GLN. I mean, every class of groups has a wonderful proof, but there is no proof in general. So what is going on here? Anyway, since there is no proof or no idea of how to prove it, what we did is Male, Isaacs, Gunther Male, and myself, we reduced to a question on simple groups. So this question, of course, implies to prove Mackay for simple groups, which, by the way, now it's known, but also much more. Equivariant bijections, a cohomology, you need to check things. It's complicated. Yes?
So in some cases where it's known, I know nothing about it, is there some hint of bijection between these two sets of the same cardinality?
In some cases, there are some natural bijections. For instance, symmetric groups P equals 2, GLN P equals 2, but in general, there are no natural bijections, although we expect the bijections to be that commute with certain Galois automorphisms. We expect the bijections to commute with certain automorphisms. We know a lot of what is going on, but no proof. So what we did was to reduce it to a question on simple groups, and the whole highlight of this subject is the theorem that for P equals to Gunther Male and Britta Speth, they prove that these conditions for P equals 2 hold, and therefore that the Mackay conjecture is true for P equals true. What is going on for P odd? I'm not the right person to ask. My job was done here. Now it's in the hands of the specialist in simple groups. Okay, so P prime degree characters can be counted locally in a wonderful way. Defect zero characters, as I told you in the previous talk, they cannot be counted. Imagine that your group is a P prime group. There is no local. If P doesn't divide the order of the group, every character, the P part of every character is 1. And the same happens for the group. So every character has P defect zero character, and here there is no P local structure. So P defect zero characters they are different. But what about the rest? For instance, let me write down 4 equations, okay? The first equation is, I'm going to write, suppose that GP is P to the A. I'm going to write a few equations. Some of them are silly, but okay, I'll make a point out of this. The first equation is, first of all, I want to define the defect of a character. So if we are trying to count characters, defect is the right concept. So let me give you the definition. So if you have an irreducible character of a finite group, and you have that d is an integer, then we say that chi has defect d if the p part is p to the a, well, let's write, or the p part of p times p to the d. Okay, let me put it here. So this is what we call the defect of the character. Of course, defect 0 means that the p part is the full p part, so it's what we had before. And usually, this is dates notation. Kd of g means the number of irreducible characters of defect d. So for instance, if the p part is p to the a, what is ka of g? Well, these are the characters, the number of characters, such that the p part is the p part times p to the a, but it's the same thing, so this is 1. So ka of g is the number of p prime, the number of p prime characters of g. So k of g is the number of p prime characters. K0 of g, as I said before, is the number of defect 0 characters. Just to play a little bit more, what is K1? K1 of g is the number of irreducible characters of g, such that the p part, well, is not the full p part. Full p part would be defect 0, so divided by p. So 1 less. Okay, you're getting the sense of defect, right? So I'm going to write, as I said, like a few equations, which are the following. First equation is Ka of g is the number subgroups of g of order p to the a of, I'm going to have these coefficients all the time, and I hope that you don't mind. Okay, when I'm going to be running over p subgroups. When you run over p subgroups, I mean, you have the whole conjugacy class of p subgroups. Some people prefer to use here representatives, G representatives. I prefer to work with all of them, so I have to always to put this coefficient because I'm running, I mean, how many are here? How many are here is the index of the normalizer, okay? So I prefer to work over all and then to correct. You understand what I'm saying? I mean, you can just run over the representatives, but I prefer to write it like this. Okay, so this equation is what? Well, this is the number of p prime characters of g, as I said before. This is the number of p prime characters. Oh, what is this? Oh, the size of the p subgroup is p to the a, so this is a CeLO p subgroup in this case. Okay, so what I'm writing down here is just the Mackay conjecture in a silly, different way. Everybody sees that? Ka of g is the number of p prime characters of g. I'm running over the CeLO p subgroups. This cancels, and this is the number of p prime characters of the normalizer. Okay, so this is the Mackay conjecture. So this is deep. Let me write another equation. This is not so well known, so let me write it down. K1 of g is the sum I run over the p subgroups of g that have size p. I do, all the time I have to do this, because I'm not running over representatives, and then I put K1 of the normalizer in G of p. Okay, so I'm counting, if this is true, I'm counting characters of defect 1 locally.
Gabriel, I have a question. You
Yes.
wrote that inequality We don't know that equality, so that's
No.
a conjecture.
That's the Mackay conjecture.
There are four equations.
Yes.
So
This is
conjectures?
some of them are conjectures, some of...
Well, it's confusing.
Yes, okay, I will explain. The first one is...
You write equals usually.
No, I write equal, so this is a reformulation, this is equivalent to the Mackay conjecture.
I understand that, but...
Yeah, so this equation is Mackay conjecture. Yes. Now my second one, this is my point here, it's a theorem. This is true. This is a theorem of Richard Brauer. He didn't state it this way, but I redid things and it's okay. This is deep. This is about blocks with cyclic defect group.
But if P divides the order of the group to power 1,
No. Well,
in that case, this is Mackay again.
yes, of course. Okay. So you see the pattern. By the way, if I put 0, then this is not a theorem, this is just silly. Because if I put here p to the 0, p to the 0 is 1, so I just have a silly equation. Okay, so now you see the pattern, right? That would be the answer to the main problem that we are working on, just to count subgroups of defect, subgroups of order p squared, to count number of characters of defect 2. That would be wonderful, but it is false. So, for instance, K2 of G is not, in general, the sum P equals P squared, normalizer in G of P, divided by G, K2 of the normalizer of P. The first counterexample is just D8. If you think about it, we are trying to count it even in P groups. In P groups, the character degrees of D8 are 1, 1, 1, 1, and 2. So the 2 is the one that has defect 2. And here, how many subgroups do you have of order 4? There are 3 subgroups. Okay, you do the thing, and here you have a 1, and here you have a 3. All these 3 subgroups have normalized the whole thing. So this is wrong. So we have to think on something else. Okay, in order to tell you the story, now I have to make a detour. So things were like this. We had the Mackay conjecture, and suddenly, 13 years after, Alperin came with another wonderful conjecture that everybody thought that it was not connected. So let me tell you about Brauer's Alperin weight conjecture. Am I using this? Okay. So this is Alperin weight conjecture. If this is the first time that you are hearing Alperin weight conjecture, you might think why he thought on this, but there are reasons. Let me try to explain. So suppose that G is a group, and what Alperin did was he add P subgroups. If I don't take representatives, I always have to divide by the coefficient. And he considered the number of defect 0 characters of these quotients. It seems that in groups of Lie type in characteristic P, these are called the weights. These are characters of this quotient that have defect 0. Is this clear for everybody? Yeah, we know what K naught of G is, K naught of this factor group. So what Alperin conjectured was that this was what we call L of G, and this is simply the number of conjugacy classes of G of elements whose order is not divisible by P. Or, in other words, because we're talking about representations, is the number of modular representations. So this is also the number of F representations, F irreducible representations of the group G, where F is, well, for instance, where F is algebraically closed of characteristic P. In this case, L of G has two meanings. You can think of L of G as group theoretical, but also its representation is an invariant of representation theory. And it makes more sense when all these conjectures have version for blocks, and when you do the versions for block, it makes more sense to talk about representations rather than conjugacy classes. But if you want just a very simple statement with conjugacy classes, that's Halperin's Wien conjecture. I also think that he was inspired by Okuyama. This is just for the experts. There is something called the vertex of a Bravach character, and Okuyama proved that the number for p-solvable groups, that the number of Bravach characters of vertex Q is the same as the number of characters of vertex Q of the normalizer of Q. This looks like the green correspondence. This is for the experts, but for reducible characters. This is not true for finite groups in general, only for p-solvable groups. This, if you know about Bravach characters, these are the weights. These are weights. Anyway, so we had Halperin Wien conjecture, and what has to do with counting characters, ordinary characters of G? Okay, let me tell you. By the way, let me write Halperin's Wien conjecture in a different, silly way, which is to put, remember that we are summing over all p subgroups. Let's put the trivial one and then the rest. So this means that L of G minus the term. What is the term for the trivial subgroup? Well, if you put p equals 1, then what you have is k naught of G. The normalizer of 1 is the whole thing. So this means that LG minus the number of defect 0 characters is exactly the sum, p bigger than 1, that my factor, k naught, the normalizer of p. So what I'm writing this silly equation just to put one term on the left-hand side and the others in the right-hand side, because this is local. This is normalizers of p subgroups divided by p. So this means that this quantity is local. I will define local sometime, but not now. Local means calculated in proper subgroups. Okay, this was 1986, I didn't say that. And in 3 years after, Jeff Robinson and Reinhard Knorr, two of my favorite mathematicians, they just came out with a wonderful idea, which is to introduce chains into this problem. Chains were already introduced, chains of p subgroups. I will explain, I will define. Were already considered by Brown, by Quillen, and many others. But not in the context of local counting. This was Jeff and Knorr's and Jeff idea. So now I'm going to go very into elementary group theory, so I hope that nobody minds. I'm going to define chains, and I'm going to define some functions which are very special here. The other day I missed a nice little lemma, so I don't want to miss today like nice little lemmas. Okay, I think I'm okay. Okay, so now it's chains. So what is a chain of P subgroups? Well, suppose that G is a finite group G. P is our fixed prime. And I'm going to consider a chain is simply, you can do this in the language of simplicial complexes, etc. But I'm just going to do as much as very algebraic, with algebra, all the time with algebra. So this is simply, well, this is a chain of P subgroups. The PIs are P subgroups of G. The only thing that I'm requiring is that the inclusions are strict. And I say that the length of the chain is n. As Date likes to say, the number of inequalities, right? So here I have n plus 1. So this is the size, the length of the chain. And of course, I can conjugate chains. So if G is in G, I can conjugate my chain. And I have another chain. This is C to the G. And we have an action, of course, and we have a stabilizer. So I'm going to call it, when you deal with chains, there are two ways of defining, to denote the stabilizer. One is this, the other is this. But anyway, this means, the stabilizer means the intersection, the elements of G that fix the chain is the intersection of all the components. So I will consider this also local, is intersection of P subgroups. So this is the stabilizer of the chain. There are several different types of chains. I'm going to call C of G these chains, all chains. These were considered by Brown. I'm going to be using normal chains. These were defined by Robinson and Knorr. So these are the chains. So these are the chains. In which Pi is normal in Pn for every I. You can consider, if you want, elementary chains. These are elementary chains. I think these were considered by Quillen, and these are just chains in which the Pn is elementary abelian. Of course, an elementary chain is a normal chain, etc. So here is the theorem. I will prove a part of it. Okay, so here is the main idea, is the following. I shouldn't be erasing Alperen conjectures. That's a shame. Okay. I will erase Mackay. I didn't say that there is a reduction for simple groups, that there is people working on this too. But if Mackay is still not done, Alperen conjecture is far from being done. Okay, so here is, I'm going to be interested in functions. I have a problem writing this, but I hope that nobody gives me a nightmare. So this is the collection of all finite groups. Whatever, all finite groups. So these are all finite groups. Okay. And I'm interested in functions that go from all finite groups to the integers. In fact, I'm interested in more functions going to a billion groups. But for the purpose of this talk, I'm interested in functions that go from all finite groups to the integers. For instance, fg can be the number of defect 0 characters of G. Fg can be the number of p-regular classes. F of G can be the number of composition factors divisible by p. F of G, you can imagine any function, the number of CLOP subgroups. It can be whatever you want, or size of the normalizer. So I want constant on the isomorphism classes. So I want that fg1 equals fg2 if g1 is isomorphic to g2. So I'm interested in this kind of functions. And once I have a function like this, I'm going to define a new function. Okay, I'm going to call it f star. So f star is going to be another function. And f star of g is the sum. So I take all the chains. Every chain has a length. So if it's a positive, so if it's even, it's going to be a 1. If it's odd, it's going to be a minus. I have to always to divide by my correcting factor and f of gc. Okay, just bear with me that this is a very interesting function. You have a function, and then you define this new function. So far, so good? Just a definition. Why is this important? Well, first of all, let me prove a theorem for you. So theorem. If I take the sum, if I take normal, all the chains of if I take normal chains, or if I take elementary chains, or if I take the so-called p-radical chains, the answer is always the same. And this is what I'm going to prove. F star of G equals 0 if OP of G is bigger than 1. For those of you, OP of G is a normal, the largest normal subgroup. So this is the largest normal subgroup of G, such that the order is a power of P. Both proofs are similar. And when you are dealing with chains, the trick is always to pair chains that have the same normalizer. Ones that are odd, the others are even, you kill them. That's always the same trick. Okay, so I hope that it's okay to prove this. So it's very elementary, but I will just sketch the proof. Okay. And you get a taste of chains. It's very easy. So proof, I'm going to prove the second part. So I'm going to call L to be OP of G. I have any function f from the collection of finite groups that is constant on isomorphism classes. And what I want to prove that if L is bigger than 1 and G is a finite group, I want to show that f star of G equals 0. So this is my aim. So how do I prove that? So here's a trick. Whenever I have suppose that C is a chain, well, P1, Pn. So suppose that this is a chain, and I'm going to construct another chain, C star. What is C star? Well, if Pn, if L is not contained in Pn, my chain C star is going to be add this term. Because L is a normal subgroup of G, you can multiply by any P subgroup and you have a new chain. Notice that this is strict because Pn cannot be Pn, because otherwise L would be contained in Pn. Okay? But it might happen that L is contained in Pn. Then I choose a place in which I need a bigger picture here. So if it's contained, there is some n in such a way. I mean, I take the smallest one. Suppose that L is contained in Pn, so L is contained in some Pm, but not in Pn minus 1, because L is not 1, right? And then what I do is, okay, this is a little tricky, but this is when you study chains, that's usual trick. So I do one of two things. If Pm minus 1 times L equals Pm, then I delete Pm. And this is my new chain C star. So if Pm minus 1 times L equals this one, delete it. If it's not, add it. Add it means add LPM minus 1. And it is very nice and easy to check that if you do C star star, you get what? C, right. Just think, I don't know, for instance, imagine that you are in this case. If you are in this case, this is your C now. Look at your C. Is L contained in here? Yes. It's, where is well, Pn times L equals Pn. And then you have to delete it, so you go back to C. Okay. But the nice thing of this pairing is you can check very easily that they have the same stabilizer. You check that when you do the intersection of the normalizers, using that L is normal. L is doing nothing. It's not contributing to anything. And the nice thing is that minus 1C equals minus 1 minus 1 C star. Right? Because in every case, it has one or one less or one plus. So when you are adding all this sum, when you are doing all this sum, you can do it using C's or using C stars. So this quantity is the same thing with a minus. So this quantity should be 0. Okay? So I'm leaving some details here, but this implies that f star of G equals 0. This reminds me of the function. I proved the other day that the number of defect 0 characters is 0 if OP of G is bigger than 1. So K0 wants to be the star of a function, but we will go into that. Okay, so here is my f star function, and I want to say that a function, and this is a big definition for me these days. In fact, I have discovered that also Jacques Thévenin have the same definition, which is good. So my main definition is that a function is local if f star equals 0. Why this makes sense? Why to call this local? Because something is happening if f star is 0. If you have a function and the star is 0, go to the function. Put here, consider here the chain, the trivial chain, and put it in the left-hand side. Well, by the way, if OP of G is bigger than 1, then f star of G is 0, so as I proved, so this is not an interesting case. So suppose that you have a group G and OP of G equals 1, which is the interesting case. For instance, if G is simple. Then imagine that you have a local function. Then what you have is that f of G, right? Put C equals 1 here. If you put C equals 1 here, this is 0, this is 1, so you can put it in the right-hand side. So you have that f of GC is the sum chains not 1, of minus 1, C plus 1 of my coefficient. It's always bothering me, but I prefer to have it there, of f of GC. And what is f of GC? Well, f is any function, but this is a proper subgroup. This is the normalizer of a chain. So this is normalizing every term of the chain. The smallest one, for instance, is normal here. The smallest term of the chain is normal in here. So this group cannot be the whole group G because OP of G is 1. So what I'm saying is that you can calculate your function G if you know your function in some special subgroups. Okay? So this is why I call it, yes. Excuse me, what?
Why do you have this exponent order of C plus 1?
Oh yeah, because I put 1, it comes here. And it comes with a minus. Right? If you put C equals 1, this is a 1. I put it in here, it's a minus, so I multiply by minus 1, and then the others get plus 1 here.
So this equal to if
Yes, 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 exactly. It's an if and only if. F is local if and only if this equality holds, because you put F in the right-hand side, and then you have f star of G equals 0. This is clear? Yes. So now, Marty and I, we are playing on which functions are local. And let me confess something. Chains for me were a nightmare. I have spent much of my many years trying to find a Mackay conjecture to count not characters of p-prime degree, but characters of other defect. It has been impossible. I had always inequalities. I never had the right equalities, except for the case D equals 1, which is a theorem of Brouwer. Chains are, let me say it clearly, terrible, in the sense that if you want to compute chains, there are too many. There are many, many chains. But suddenly, with the help of Thomas Breuer and my son, I have a powerful code for chains. So now you give me a function, a crazy function, and I will tell you if it's local or not. Like this. So right now I know that some functions are local, some functions are not, and I'm playing with this. Okay, but it's not time still to announce anything. I'm just saying that we're having fun. Okay, so I don't know. I can cook many functions. Number of composition factors of divisible by p. It's local or it's not local. I go to the software. I say no, it's not local. Oh yes, it's local. Oh, perhaps meaning I just check as many groups as possible, and I can make a guess. This doesn't mean anything, but it points me in the right direction all the time. Okay, so this was a small confession. Okay, so why this is important?
I have a question.
Yes.
You don't find the topology part of this? I mean, these different complexes are homotopy equivalent, and there's all of that machinery. You don't find that useful?
Very good question. Very good question. I still have not studied that. I don't know. If it's contractible, if it's, I don't know.
Right.
Perhaps, can it help?
Like an Euler characteristic. I mean,
Yes, Euler characteristic, exactly. Yes, for those of you that know algebraic topology, I'm not one of those. You see that there is algebraic topology here, homotopy equivalent, simplicial complexes. Can this help in order to solve all these conjectures? That would be wonderful. But I'm still in another stage, I think. No, but I mean, of course, it's a fantastic question. Okay, so what this has to do with what? Okay. Then I have to prove a theorem, so I hope it goes fast. And this is the famous Knorr-Robinson inversion. So this is the Knorr-Robinson inversion. So this is a theorem that says, suppose that you have a finite group G, and suppose that Alperinway conjecture holds for smaller groups, for X with X less than G. I'm working by induction. Suppose that Alperinway conjecture is true for every finite group with order less than G. Then Alperinway conjecture holds for G if and only if K naught of G is, let me write it first, sum of chains my coefficient. Jeff and Reinhardt, they choose to work on representatives. I prefer to work like this, but it's the same thing, of LGC. Or in my new language, if and only if K naught of G equals L star. L is the number of irregular classes of this, or the number of modular representations. So let me prove this for you. So suddenly there is some function. So Alperinway conjecture is saying that K naught is L star. So the function L, such a natural function for every finite group, its star should be the number of the effective zero characters. And the proof, just a sketch, if I remember. So what is L star of G? So I start L star of G, by definition, is all these chains, okay? This is the definition. L star is this thing. So I divide it into two parts. First, the chain, which is 1. So this is L of G. And then, because I only have 10 minutes, but it's okay, I'm going to divide the chains in the following way. I take a fixed some P subgroup P, P sub P subgroup, and I take the chains. This means the chains whose first non-trivial term is P. So these are the chains, 1, P, P2, etc. You still with me? I'm just take all the normal chains. By the way, I'm using the fact that here is the same to use normal chains or elementary chains, or this is the homotopy equivalent theorem, which is, by the way, it's easy group theory. It's nothing deep. I'm going to take normal chains. I need normal chains, otherwise my argument doesn't work. Okay, of what? Okay, -1 to the C, GC, G, L of GC. I haven't done anything, right? But let me put here something. I'm going to do something. So this is just copying the other equation, but I'm going to do something else. A little bit of group theory never hurts. The number of irregular classes of G, C, I mean GC is a chain. C is a chain that has P as a normal subgroup. These are normal chains, so the stabilizer is the intersection of the normalizers. So P is normal in here. So the number of conjugacy classes of G is the same as the number of conjugacy classes of G mod some normal P subgroup. Okay, elementary group theory. I'm thinking that once I thought that this requires Sachsenhaus. Anyway, I don't have time for this. What do you think, Marty? I think it does, right? So it's elementary with Sachsenhaus or something. but this is true. Okay, and now it comes a trick. It's just a 1-minute trick, which is the following. What are these chains? I'm going to pair these chains. So these are chains that start with P, and I want to go. It's very easy. From this set of chains that start with P to the set of normal chains of the normalizer in G of P divided by P. Let me see if this is very difficult or not. So I have a chain like this. 1, P, less than P2, less than Pn. All these guys here are normal in the big one. I'm using normality. I'm using normal chains here. And then if I want, so every guy here, Pi is normal in the normal, all these are contained in the normalizer of P, right? P is normal in Pn, so Pn, P, for instance, is normal in Pn. So in Pn, in P2, in everything, so Pn is really contained in the normalizer of P, right? Because these are normal chains. I'm using normality here, right? Normal chains means that P is normal, that P2 is normal, that everything is normal in everything. So they are all normalized in the CELO P. So how can I get a chain of the normalizer of P mod P? Very easy. I just do, well, first is P mod P, P2P, PNP. Yeah, this is a chain here. I'm going to call it again, if this is the chain C, this is going to be the chain C star. It has one less term. And what is the stabilizer in this group? This is a nice fact. What is the stabilizer of this chain? Okay, in this group. So how do you calculate that? It's the stabilizer in this group of this chain. Well, it's just the normalizer of all the terms divided by P. So this is just GC over P. The stabilizer of this chain is this. So I know, now I go to that big sum. Yeah, okay, let's go here. I go to that big sum, and I have that this L of G plus 1 over P. And now bear with me, I want to go to chains in the normalizer of G of P over P. But I have to do a little bit of fixing things. First of all, with this bijection, my chain is not, well, it's C minus 1, remember? I have a bijection, but the sign has been changed, so I have to put a minus 1 here. What else do I have there? I have GC, okay, 1 GC divided by P. So I need to divide by P upstairs. So it's G divided by P. I haven't done anything, right? I have divided by P and by P, so it's okay. Right, so far so good. But I want the normalizer here, so I'm gonna put the G over there. Okay, let me do it in 2 steps. So this is GC of P. and now I go full. So the minus goes in here, and here the G goes outside. And here what I have is what? What I have is sum over all the chains, the minus is outside, and here you put, well, let me do it in 2 steps. The sum of all the normal chains of -1 to the C, and this is the stabilizer of the chain divided by the order of the group of L of G, C, P, which is exactly the normalizer of this chain, the stabilizer of this chain. Okay, so if you look at this, because P is bigger than 1, you are in a smaller group. So this is L star. So this is L star of this group. Look at the definition of L star. So this is L star of this group. Okay, so I'm going to write it here. So this is LG minus the sum 1P, normalizer of P over P, of a G, sorry, of L star of this group. But by induction, L star is K naught of this group, by induction. So this is LG minus the sum 1P of, by induction, K naught of the normalizer of P, P, I shouldn't forget my coefficient. Oh, but I'm very close to Alperen-Wave conjecture. What is it? Oh. You see, L of G is the sum of all P subgroups of this quantity. So here is all P subgroups except 1. Okay, so I add it and subtract it, right? So I have to put P equals 1. If I put P equals 1, I have to subtract it. And now I have it, because all this comes from L star of G. Okay. So this is exactly what we're looking for. Yeah. And sorry I rushed a little bit, but I wanted to finish this. So suddenly, let me recap here. Suddenly, Alperen-Wave conjecture that was something else becomes as the following conjecture. The wonderful function L, which is counting number of irregular classes of elements of order not divisible by P, Alperen-Wave conjecture says that L star equals K naught. Okay, and I will stop here.